Hello. Today we're going to do a new technique for integration called integration by parts. And this is our last way that we can integrate stuff. If you move beyond integration by parts, there's some other like kind of funky algebraic stuff, but this is basically it in terms of, even moving further along in calculus. There's nothing else. So other than using Riemann sums and maybe a couple of other like insane algebra tricks, this is the end of what you can integrate. So I'm going to show you the proof second. I'm going to show you what it is first. So integration by parts is something you're going to use when you see a problem that has usually two things multiplied together. It's kind of a way to undo products. It's almost like a reverse product rule of sorts. So an example of it would be a problem that looks like this. If you look at this problem, right now there would be absolutely no way. There's nothing I can let equal u. I have nothing inside anything else. There's no way to rewrite cosine as anything else. So it's a really straightforward and simple problem, but yet I don't have any method to do it at this point. So when I see something like this, I'm looking at picking out two different parts. One of them I'm going to call u, and the other one I'm going to call dv, or the derivative of v. Sometimes I hate using u and v because they can look similar when you draw a u and you draw a v, but just be careful because, and I'm going to keep using u and v because that's what every book you see is going to use. So down here I'm going to write out what it is, and then I'll go and do the proof later. But integration by parts says if you have the integral of one thing multiplied by another, one of those things I call u, and one of those things I call dv, or the derivative of v. So up here, what I'm going to pick is I'm going to let u equal x, and I'm going to let dv equal the cosine of x with respect to x. So I'm going to replace all parts. I'm going to replace x with u, and I'm going to replace the cosine of x dx with dv. Making no sense to you yet, but that's going to force this problem to fit the criteria of what integration by parts is going to require, so that I'm going to be able to turn my problem into u dv, just like this has. So integration by parts says if I can split my problem into two parts, call one of them u and call one of them dv, I'll figure out what u is, I'll figure out what dv is, and then I'm also going to figure out from there what is du and what is v. So this is going to require integration and taking a derivative all within the same problem. Whatever I pick to be u, I'm going to figure out what the derivative of that u is. And whatever I pick to be dv, I'm going to figure out what the integral of that dv is. So if I were up here doing an actual problem, if I let u equal x, du is going to equal 1 with respect to x, and v is going to equal sine of x. Technically plus c, but I'm not going to really worry about that right now. So what I just did was I allowed u to be this and dv to be this. I'm also going to need these expressions. So to find them, I take derivatives and I take integrals. I'm going to need my given u. I'm also going to need an expression for the derivative of u. I'm going to need a dv, and I'm also going to need an expression for v itself. These four things are going to go into the formula for integration by parts. So the rule for integration by parts says if I have the integral of u dv, this is going to equal u times v minus the integral of v times du. That's a fact. I can prove that in a minute. But what integration by parts is almost using substitution and a new integration system. It really is a substitution as well. I mean, I'm taking out x, replacing it with u. I'm taking out cosine x dx, replacing it with dv. And now I have these other symbols to use to replace all this stuff. So I know what a u is, I know what du is, dv is, and v. I'm going to plug all of that into my formula. So when I am finding the integral of u dv, which is now what I have, that's going to become u times v. So if I go up to the problem, I have u times v. I'll write it out like this: u times v minus the integral of v du. Okay, let's go put in what that actually is. U times v is x times the sine of x minus the integral of v du. Well, now I just gave myself another integration problem, but it's an OG problem. It's an original, easy integration problem to do. So I'm going to keep working through. So therefore, this equals x times the sine of x. The integral of sine is negative cosine x. And now I'm finished my whole integration problem. I have a plus c. That is the answer. This expression is what I would get when I take the integral of that. And if we wanted to check ourselves, we could. Okay, so I can check myself, and I can check and make sure that the derivative of this does indeed give me this. So let's see, with the derivative of x sine x, this is a product. So the derivative would be the first term times the derivative of the second plus the second times the derivative of the first. The derivative of cosine is negative sine. The derivative of c is 0. Well, check it out. It gives me x cosine x plus sine x minus sine x, cancel, cancel, plus 0. It gives me what I started with. It worked. So some person sat around basically with a product rule and just did a lot of guessing and testing and checking and a lot of thinking to figure out how to manipulate a product in such a way to give me a problem that I can work with, and it's going to work out every time. Crazy. So to recap, the formula for integration by parts is if I can take an integral and change it into the product of two parts, u and dv, then that will equal u times v minus the integral of v times du. This is what we call integration by parts. Yes, it's another formula to memorize, just like you memorize product rule, quotient rule, or any of those things. And let me tell you, if you want to know where it came from, now let me do one more example and I can tell you where it came from. So let's do this one. Let's do the integral of x e to the negative x dx. Let's make this one a definite integral so we can practice that fundamental theorem of calculus. So a little hint, when you're trying to figure out what u is and what dv is, u is typically the thing that reduces in power, but that's not a steadfast rule. It just usually, that's how we would want to pick u first. I'm going to have these two parts, x and e to the negative x. One of them has to be u, one of them has to be dv. So u is typically the thing that will reduce in power, when I take a derivative. Okay, so in this case, my x to the first will reduce in power. So x is what I'm going to pick for my u. So u is going to equal x, dv is going to equal e to the negative x dx. All right, now both things have to be differentiable, which it will be, and integratable, so that can sometimes be a stumbling block. But right here, we're okay. So the derivative of u is 1 with respect to x. The integral of dv, I wish we were together, because I could say, why am I taking the integral? Well, I need to find an expression for v. So the integral of the derivative is the original. We haven't talked about that this year. We talked about it a lot last year. So the integral of 1 dv is v, and then take the integral of the other side, and I get e to the negative x divided by negative 1. Or if I were to write that a little nicer, or more nicely, whatever, I'd have negative e to the negative x. That's what dv is, or that's what v is. Okay, so use the formula for integration by parts. I'm not going to write this out every time, although it's not a bad practice, so you start to remember it. But u times v minus the integral of v du. Clean this up a little bit, and I have negative x e to the negative x plus the integral of e to the negative x dx. I have to actually do this integral. Notice I'm putting away the limits for right now, and I'll come back to them in a second. So negative x e to the negative x plus the integral of this is e to the negative x divided by -1. I'm just going to make this a minus. I don't need to have a plus c on here because this is a definite integral. I'm evaluating from 0 to 3. Again, if I go back and I wanted to check that, you could pause it and check it. Now take the derivative of this. Do you get back to the original? And you will. All right, now sometimes people feel like the plugging in of these numbers is weird. Notice like I'm not putting the 0 to 3 throughout the problem. It just gets messy. I'm going to wait till I'm finished and then remember, oh yeah, I'm integrating from 0 to 3. So then I plug in 3. So I have -3 e to the -3rd minus e to the -3rd minus 0 minus e to the 0. So when I finish, I'm running out of room. This is going to become -3 over e to the 3rd minus 1 over e to the 3rd plus 1. E to the 0 is 1 minus 1. And if I really want to be as simplified as possible, I have the same denominator here. So I'd say -4 over e to the 3rd plus 1. Isn't it crazy to think that what that means is that if you were able to graph that original function, y equals x e to the negative x, and evaluate the area under that curve from 0 to 3, the area would be that number, -4 over e to the 3rd plus 1. That's so crazy to me, but I love it. Okay, so as promised, I wanted to tell you where this came from. I'm going to come back and do one more example problem. No, fine, I'll do the example now. That way, if you want to just block out the proof, you can just shut it off. So the last one that I love is the natural log. So now we can finally take, not finally, I know you haven't been like waiting all this time, the integral of the natural log of x. Think about, we couldn't take that integral until now. There was nothing, I have no formula for that. I have no way to take that. Well, if I let u equal the natural log of x, dv can equal 1. Pause the video for a second, or don't pause it yet, but you might not have thought integration by parts when you saw this, because you might not even have thought there was like a product, but there is technically the natural log of x times 1 dx. Pause it and see if you can go through the work and actually get to what you think the integral of this will be. All right, I'm going to start it now, but it would be a good one to go through and see if you get it. So the derivative of natural log of x is 1 over x. The integral of this is x. So you might think, oh crap, like we're going in the wrong direction. The antiderivative of 1 is x. So like I'm adding more to the problem, but let's see what happens. So follow integration by parts. We have uv minus the integral of v du. So clean that up. X times 1 over x. Don't lose the integration sign. We did not integrate yet. So we have x ln x minus the antiderivative of 1 is x plus c. Boom. There's the integral of the natural log of x. And again, if I wanted to check that, I could. And it would work. So if I check it, I would have the first times the derivative of the second plus the second times the derivative of the first minus the derivative of x plus 0. So x over x is 1. This is 1, cancels with this one, and I'm left with ln x. Holla! Okay, so there is one other thing to do with integration by parts, and that's sometimes they have the repeated use of integration by parts. I'm not sure if I'm going to do it or not for today. I'm not. So for today, I'm going to stop it at that, other than showing you the proof. because I don't know that that's going to show up on the AP test anymore. So I'll check back on that one. You are going to have an assignment, so that'll be up on the thingy as well. But here's the proof, if you were curious. It's actually only algebra for the most part, which is so cool. So for the proof of integration by parts, we start with thinking about the product rule for derivatives. My kids are so loud. What are they doing? Anyway, doesn't matter. Okay, so let's think about the product rule for derivatives. Let's say I want to take the derivative with respect to x of uv, u times v. If I want to take the derivative of u times v, that would result in the first term times derivative of second plus second times derivative of first. So the u times the derivative of v with respect to x plus the v times the derivative of u with respect to x. So we all agree that's the product rule, right? Product rule written out in a formal way. Oh, this light's getting bad for you guys, isn't it? Hold on, let me shift. Oh, for the love. Everything just fell off my desk. Okay. So this requires us next to take that product rule for derivatives and integrate both sides with respect to x. So I'm going to take the integral of both sides, which I'm going to integrate both of these terms separately with respect to x. So therefore I'm going to, I lost my marker. ¿Dónde está la marker? Oh my gosh, I dropped behind my thing and now I can't find it. Oh well, you're going to get everything written in brown because I lost the other marker. So I'm going to take the integral of both sides with respect to x. So I'm going to take the integral of this with respect to x, take the integral of this with respect to x, and take the integral of this with respect to x. Okay, I'm going to rearrange this. I'm going to put this on that side, and I'm going to put this on that side. And I'm actually gonna get my negatives to be better. So let's see, I'm gonna bring this over here. So I'm going to have negative integral of u dv dx with respect to x equals the negative integral of the derivative of uv with respect to x dx plus the integral of v du dx with respect to x. Okay, I don't like the negatives this way. I would have, rearranged them a little bit differently, but I'm just going to multiply everything by -1, both sides. So this will become positive, that will become positive, and that will become negative, setting it up to look like what it's going to end up looking like. And now I'm going to go through a little bit at a time. Well, here I have the integral of u dv over dx with respect to x. Well, these cancel. So this becomes the integral of u dv. Over here, I have the integral of the derivative of uv with respect to x. So these can cancel just like on the other side. But what is the integral of the derivative of uv? The integral of the derivative, they undo each other. So the integral of the derivative of uv is just uv minus the integral of v du with respect to x times dx. These can cancel, so I have minus the integral of v du. And that's integration by parts. It's a little wonky, the whole I'm putting in dx's and some of the dx's are, the dx's cancel. I guess one could ask, why did we do it? But we did it so that I could get everything in terms of u's and v's as opposed to having any x's and dx's. But there you go. That is the proof for integration by parts. Try the practice problems, and hopefully you don't feel totally perplexed.